right, our last unit in this class, full unit, is which we're going to take a test on is gases, gas laws and gas properties. We're going to start off first today talking about properties of gases. A lot of this stuff you probably already kind of know, but a lot of this deals with what's called the kinetic molecular theory, where we're investigating gases at the molecular level and how we know some relationships about them can affect their properties and what that leads to. All right, the homework after this lecture will be to do the next 2 pages in your packet, which are not numbered, but they're the 2 pages that follow this exact lecture, which I'll show you at the end of the lecture. And then I will have an answer key supplied after the videos for the virtual students or absent students in honors chemistry. Okay? Now, the first property we're going to investigate is looking at the relationship. So up here in example number 1, we can see a container that has got described by 5 particles. And those 5 particles at the macroscale level, 5 molecules could also imply maybe 5 moles of gas. So we got a specific number or molecules of gas particles or moles. Now the temperature is at 25. A rigid container, the word rigid for this sake of this unit means that the volume is constant. The container is not flexible. So whatever it is now, it's going to stay that. So it's a constant volume. And the pressure is at 1.2 atmospheres. We measure pressure of a gas in ATM, which is atmospheres. We can also measure it in another unit called millimeters of mercury. We can measure it in another unit called torr. Okay, and the last one is kilopascals. These are all units of measurement of pressure that we could utilize, and all of these units are on the Chem Helper. 1 atmosphere is called standard atmospheric pressure at sea level. So at sea level, we're not any elevation above it. On a normal day, it's going to exhibit about 1 atmosphere of pressure. Wisconsin's not at a very high elevation, so on a typical bluebird sunny day, the pressure, atmospheric pressure, is pretty darn close to 1 atmosphere. 1 atmosphere is exactly equal to 760 millimeters of mercury, which is also equal to 760 torr. So a torr and a millimeter of mercury are equal units. They just have different units. Actually, it's named after Torricelli, who was doing investigations on mercury and pressure. And that's where we also get millimeters of mercury from. And last one is 101.3 kilopascals. But again, 1 atmosphere is the same pressure as 760 torr. 1 atmosphere is also the same pressure as 101.3 kilopascals. So these are all equal to each other, and we can simply convert from one unit to the other in any problem we do for the sake of this class. Well, in this first property we're looking at here is the container stays exactly the same volume. What we've done now is you'll notice that there are more molecules of gas. If we count, we've gone from 5 in this picture to now 10 in this picture. We have doubled the number of molecules of gas, or doubled the number of moles, which again, little n in this class, little n stands for moles of gas. So I've increased the number of moles, or increased the number of molecules of gas, while keeping the volume and the temperature constant. So the temperature is not changing, the volume is not changing. So if I, in essence, put more air into the container, what is that going to do for the pressure? What do you think? Will the pressure stay the same, or will it change? And hopefully, you said it would also increase. There is a direct relationship between the number of moles of gas and pressure if volume and temperature are constant. And you've seen this before, okay? When you blow into a balloon, when I put more air into it, it expands, because there we have a flexible container. We don't have a rigid container. And because of that, the pressure stays the same, but now the balloon increases in size because there's more gas in it. When we think of pressure in this class, when we think of pressure in this unit, you want to think of collisions. the collisions of the gas to themselves and the collision of the gas to the walls of the container. If there are more collisions, there's going to be more pressure. And that's exactly what happens in this container. By doubling the number of moles of gas, there are going to be twice as many collisions with the walls of the container, which is going to double the pressure. So there'll be an exact direct relationship between pressure and moles. Okay? So that's something that that's the first exact concept that we can go over. Now with that we can get an equation. And the equation is that if I have the pressure divided by the moles of gas, P1 over N1 equals P2 over N2. Whenever we have a direct relationship, we can always create a proportion. There's a direct relationship between two properties, we can create a proportion. So the pressure and number of moles in the first container will equal the pressure divided by the number of moles of the second container. If I plug in the variables, both of these should divide and become the same exact number. And that is the case whenever we have a direct relationship. So this is an equation we could utilize to look at the relationship between number of moles and pressure of a gas. Okay? All right, so now we have a flexible container. And now we're looking at the next relationship. So in this relationship here, we are going to increase the temperature. And we have a flexible container. So now we are looking at the relationship between volume and temperature of a gas. What we are going to keep constant in this example is we're going to keep constant the number of moles or molecules of the gas. The n variable is going to be held constant. Okay, and the pressure is also going to be held constant. Okay, but all we're going to do is we're going to change the temperature of the gas and see what happens with the volume. Now think about this logically. If I increase the temperature, what's going to happen to the movement of the gas molecules? Hopefully you're thinking to yourself, the molecules of the gas are going to move faster. And if they move faster, they are going to collide with the inside of the balloon more often. And if there's more collisions, there's more pressure, which is going to cause the balloon to increase in volume. So the balloon is going to get bigger because the average molecules of the gas, I'm going to draw it as a larger arrow because the molecules are moving faster on average. So because the arrow length is longer, it's traveling faster, they're going to collide more often, and that's going to cause the balloon to increase in size. That's exactly what happens whenever you blow into a balloon. But instead of being a temperature difference, it's more so the number of molecules causes more collisions and the balloon swells and gets larger. So there's a direct relationship between volume and temperature of the gas. So the equation that we get is V1 over T1 equals V2 over T2. Here's the mathematical equation we can use whenever we have a change in volume based on the change in temperature of the gas. Now, one side note to this, whenever we use temperature in this class, the temperature must always be in Kelvin. Because 0 degrees Celsius is a very common temperature. And we can't have 0 because then it becomes an undefined value in the denominator. So the Kelvin scale was developed just so that there are no negative temperatures and there's no 0 temperature. So again, to cause a Celsius temperature to become a Kelvin temperature, we just simply add 273 to the Celsius temperature, and that'll give us our Kelvin temperature. So whenever we use any gas law equation in this class, we need to make sure that the temperature is in Kelvin. And we'll see that in our next lecture where we go through the mathematical concepts of these equations that I'm showing you today. Okay, the next relationship is looking at volume and pressure. So we're going to keep the temperature constant, and we are going to keep the number of moles constant. So the number of molecules before and after should be exactly the same. So now we're going to make the volume of the container smaller. Well, if the volume of the container is reduced, what is that going to do for the number of collisions of the gas molecules to the walls? Because the container is smaller, there's less room for the gases to move around, and therefore they will strike the walls of the container more frequently, and that's going to cause an increase in pressure. So there's an indirect relationship or an inverse relationship between volume and pressure. So the smaller a container, the more pressure there will be if the number of molecules of gas is left the same. So because it's an indirect relationship, it's not a proportion. Instead, the pressure and volume of the first picture equals the pressure times the volume of the second picture. Whenever we have an indirect or inverse relationship, the product of the two variables will equal the second set of conditions, not a quotient, not a proportion. Okay? All right, and here's our last concept on questions. We have a rigid container, so again, that means the volume is constant. And we put a solid into the container and we remove all of the air. So currently, there is zero pressure because there is no gas present in the container. Okay? We then increase the temperature, and because there's no gas there, it's not going to cause an increase in pressure. However, increasing the temperature causes the solid to undergo a decomposition reaction. One of the products of the decomposition reaction is a gas. So now if we had a device to measure pressure, we would notice that the pressure in the container would increase if a gas is produced in a chemical reaction. So if more gas is produced than on the reactant side, the pressure will increase when the reaction occurs. If vice versa, if there's less gas as the reaction proceeds, then there will be a drop in pressure because there's less molecules to cause less collisions with the walls of the container. Okay? So the states of matter are very important when it comes to pressure. Only gases will create pressure in containers for the sake of this unit. If it's just solids or liquids, it will not. Okay? And if there's more gas produced, the pressure will go up. Well, here's a conceptual question to finish off in this page. How would we know when the reaction is complete in this vessel? So we're going to assume that we increase the temperature to a specific spot and we stop increasing the temperature. We allow the reaction to reach completion. What would allow me to tell when this reaction would stop? And hopefully, maybe you've identified that the pressure would stop changing. Once the pressure stops changing, that tells me the number of moles of gas have stopped increasing in the container and the temperature is held constant. So once the pressure stops changing, we know that all of the gas has been produced. And therefore, the reaction is finished. So one way we can figure out when reactions are complete is by, if they produce gases, is when the pressure of that system stops increasing or decreasing. Okay? So gases are the only state of matter to cause pressure in a reaction vessel for this class. All right, one other set of concepts I want to talk to you when it comes to gases is how temperature is related to kinetic energy. On your Chem Helper, you have an equation for kinetic energy, which is 1/2 the mass of the gas times its velocity squared. So the kinetic energy of a gas is 1/2 mv squared. If I know the mass of the gas and its velocity, how fast it's moving, and square it, That'll be the kinetic energy of a gas. Just like a car, if you're traveling in a car in Marshfield going 25 miles per hour, you have a specific kinetic energy. If all of a sudden you step on the gas, that energy from the gasoline, the combustion reaction, gets converted into kinetic energy of moving your vehicle and propelling it, and now you move at a higher rate of speed. If you increase the velocity, you cause an increase in the kinetic energy of the object. Okay? All right, so temperature of a gas is directly related to its kinetic energy. So if you have two gases at the same temperature, what you know is the kinetic energy of gas A is equal to the kinetic energy of gas B, as long as their temperatures are constant. Okay, so if the temperature of any gas is the same as any other gas, their kinetic energies are equal. Well, therefore, 1/2 times the mass and velocity squared of gas A equals 1/2 times the mass velocity squared of gas B. Well, here's the key concept. If they are at the same temperature, they have the same kinetic energy. But are the molecules moving at the same speed? And the answer is no, because they have different masses. Okay? So if we have two gases at the same temperature, the lighter gas, and we can use molar mass to figure this out, the lighter gas will have a higher speed or velocity. The heavier gas, and again we'll use molar mass to figure that out, would have a lower speed. The same thing is true on the interstate. Can a semi have the same kinetic energy as a small little compact car? And the answer is yes, if the compact car is traveling a lot faster than the big 18-wheel vehicle, because their masses are so different. The same thing with gases. If you have multiple gases at the same temperature, all of the gases have the same kinetic energy, but the lighter the gas, the faster its average speed of particles. Okay? That's a fundamental concept that you're going to be tested on, and something that you really have to make sure to understand and do the homework problems off of. The last little bit of concepts are effusion and diffusion. Effusion is if I have a balloon and I poke a little hole in it. Effusion is looking at how quickly that gas will escape out the tiny opening. The same thing is when you have a helium balloon. When you have a helium balloon and you have a normal rubber latex balloon, within a day or two, it pretty much is no longer floating up in the air. Okay? Because there's tiny membranes, holes between the membranes of the latex that the gas particle of helium can escape through it. But if you have a metallic balloon, those helium balloons that are made of that metallic foil paper, it will last weeks upon weeks because they have much smaller tiny gaps in that material, and therefore the gas escapes out of there at a much slower rate. So with effusion rates, the smaller the gas, remember this, the smaller the gas, the faster it is moving, and it will escape faster. So the smaller a gas, the faster its effusion rate. Because it's smaller, it can escape that opening better, and it also is moving at a higher rate of speed, and therefore will collide with that opening more often than a heavier gas that isn't moving so fast. Diffusion is how quickly one gas spreads through another. So I guess a disgusting example of this is when somebody passes gas, and you have that really bad rotten egg smell. Okay, that flatulence, that gas, will spread throughout the air in the room, and very quickly, eventually, how quickly it spreads out, eventually might reach someone's nose where they can detect that someone has passed gas. So diffusion is how quickly one fluid moves through another. The same example would be if you have some water and you put a droplet of red food coloring into the water, it quickly begins to radiate and spread throughout the liquid. That is also an example of diffusion, where you have a liquid diffusing through another liquid. The same thing is true for gases with gases. So the smaller a gas, for both of these, the smaller the gas is, the faster its average speed, and therefore it will have faster effusion and diffusion rates because it is moving faster, generally speaking. All right, so those are some key fundamental concepts on gases and gas properties. What I want you to do now, there are 2 pages of example problems here that I'd like you to write out and explain. These really are not mathematical concepts. They are more explanation concepts. I'd like you to go over and explain what you're seeing here when it comes to answering these questions based on the lecture you just listened to. The last page is looking at this chart, which is called the Maxwell-Boltzmann distribution graph. What a Maxwell-Boltzmann distribution graph is looking at is if I have a balloon filled with helium, if every single gas particle, and there are millions of molecules here, if every gas particle, its velocity was charted in a graph, this is what you would see. You would see a graph of the number of particles, okay, versus the speed or the velocity at which these particles are moving at. So this bell-shaped curve is looking at how many gas particles have this exact speed. As you can see with the bell-shaped curve, some have very low and some have very high, and those somewhere in the middle is the average speed of the gas particles. Okay? So this is an example of a Maxwell-Boltzmann distribution graph where all of this is charted, just like if in a large classroom of 100 students, how many kids had 100%, how many had 99, how many had 77. And charting that and seeing this typical normal bell-shaped curve is a result of very few have very low, very high. A lot of them have a velocity somewhere in the middle, resulting in this bell-shaped curve. So go ahead, read through these questions, answer them, and then check over the answer key. And if you have any questions, reach out to me. Again, thanks for listening to this first lecture on gas properties.